I'm Chris Mims. I'm the project lead with Team Curimba. This is Jeffrey Patton, Barbie Chaya, and Banke. Right. So, like you said, we're the controlled and active debris removal from low Earth orbit. That's our project. So, what we're going to talk about today: what is orbital debris? In case you don't know, where should we remove our orbital debris from? What kind of orbital debris? The choice of what orbital debris to remove, how to remove it, and then we're going to present our concept for the debris removal mission. So first off, what is orbital debris? These pictures show all the orbital debris that's currently tracked, and it's over the last 6 decades. So in 1960, you can see there's not that many man-made objects in space, obviously, beginning of the space age. And then as you progress through the pictures, you can see the amount of debris in space growing. So by the time you're in like 1990, it looks as if Earth is almost completely obfuscated. In these pictures, you can also see like 3 different orbital regions. There's the low Earth orbit is everything just around Earth. Then you have the medium Earth orbit, all of this kind of scatter. And then this obvious ring is the geostationary orbit. So one thing to note is that 95% of the objects that we're tracking right now in space are debris. And over 2 million kilograms have been left in orbit. And just to put that in human terms, that's around 1,000 cars. And it's growing at a rate of 16 cars per year. That's more debris we're putting into space. Another important point is that we're only tracking debris with a cross-section of 10 centimeters squared or larger. There is an untold amount of smaller debris that we can't track. Things like little bolts or screws or small plates. These are equally important because they're also traveling really quickly with a lot of energy, and they can cause a lot of damage. We just don't have the ability to track them as.
Do these space debris cause problems for launches? I mean, because I can't imagine hitting one of those with a rocket.
They do cause problems for launches in that right now when you have a launch, you have to choose a launch window with like the lowest amount of space debris, the lowest chances of hitting anything. It's not quite as dense as it looks. This picture is very zoomed out, and the points are clearly not to scale. But there is definitely areas where you don't want to launch. I'll go into that a little bit later.
Just add a comment.
Yeah.
Years ago, I worked on a space shuttle. Twice they had to replace the windshield. One of the windshield panels was 2 flakes that were hit by debris, and these weren't like bolt size; these were like paint flake size. But because they were doing this crossing, it's essentially hitting you at 14 or 15,000 miles per hour. So it's amazing that something just a gram will do the amount of damage that it produces.
Right. The orbital debris is dangerous no matter what size it is. So the first thing when you're designing an orbital debris removal mission is what orbit do you pick to essentially declutter? This is a really important choice because the mission design is completely different if you're going to low Earth orbit or geostationary. So we argue that low Earth orbit is our main point of focus. If you look at the first chart here, this is a graph of the predicted growth of orbital debris. If you look at the geostationary and medium Earth orbit, they're pretty linear. So there's not any, it's pretty calculated risk there that it's not going to get much worse very quickly. The low Earth orbit, though, it looks almost exponential there. The cause of that is that as the orbital debris density increases in low Earth orbit, the chance of a collision between orbital debris gets higher and higher and higher. And if any of those collisions happen, it can start what's referred to as the Kessler effect. It's like it's a cascade of debris where one collision causes more debris, and that debris creates like a debris cloud, and now your effective area of the probability of a collision happening is much larger. So that's what you're seeing here.
So stupid question, is the space station in low Earth orbit?
Yes, the ISS is in low Earth orbit. The second important reason that low Earth orbit is a high priority orbit is that nearly all manned missions, I think everything now after the Apollo program, all of those missions are in low Earth orbit. Not since the moon have we left Earth orbit, low Earth orbit. So the risk to human life there makes it so that's our priority as well. And a lot of the most important satellites operate in low Earth orbit. All the, I guess, government spy satellites, weather satellites, anything that's doing Earth imaging, it's a lot of really important satellites that you want to protect. And this is the picture at the bottom is a little bit of a dramatization, but it's a screenshot from Gravity, which was a good movie illustrating the Kessler effect and the cascade of debris collisions. Probably a little inaccurate in the time frame of that, but it just shows you how much debris can be caused by an impact. And actually, a side note, there have been between April 2012 and March 2012, there were 6 orbital debris incidents at the ISS. So 4 of those, they actually performed a maneuver on the ISS to avoid the debris. And the other 2, the crew had to retreat to the Soyuz capsule because they didn't have enough time to perform a maneuver. So in case they were hit, they had to essentially abandon the ISS. And that's not something that many people know of, but it happens quite often. So now that we picked low Earth orbit, this is a simulation that was run that calculates the predicted growth. So one thing that happened semi-recently in the space age is a kind of requirement or suggestion internationally that all future space missions should have a post-mission disposal phase. And what that is that after your mission has completed, you can't just leave it there, which in the past we've mostly done. We just leave it in orbit because there's lots of room up there, who cares? Now we're realizing that's not such a good idea, so after your mission, you're basically required to either move it higher to a parking orbit, where it's not going to cause a problem, or deorbit it into the Earth. So the red line here is continuing regular launches, with that 90% of all launches having a post-mission disposal phase. So that, it helps a bit, but you can see it's still growing at a high rate. It's not really acceptable. The blue line and the gray line there are showing the same amount of launches with post-mission disposal, but also running an active debris removal mission. The blue line is running 2 missions a year, and the gray line is with 5 missions a year. So the goal here would be eventually to remove, to lessen the amount of debris in space. But this graph shows that even with running 5 debris removal missions a year, we're basically just maintaining a constant level of debris. 2 interesting things on here. I don't know if you guys know, but the Chinese ran an anti-satellite test. They launched I'm sure you guys know. They launched a missile and blew up a satellite. And you can see the huge spike in debris that caused, just from that one satellite exploding and basically scattering highly energetic particles all over low Earth orbit. And then the inactive Cosmos satellite collided with the Iridium-33, which is a communication satellite. And that also contributed to that quite a bit. So you can't just say space is big, it's not going to happen. It's already happened, and it will probably continue to happen if we don't do something about it.
So, just a question. So
Yeah.
Earlier you stated the size of what can be detected.
What can be tracked, right?
Was that volume or was that square inches?
It was square centimeters, because it's a radar cross-section, so it's the apparent size on radar. And since you're scanning it, essentially, you're looking at a picture, you can't get the depth. So if it's rotating randomly or whatever, that'll shrink or grow your radar cross-section, depending on how its attitude when you're scanning it.
So the plots that you just showed are based on what can actually be detectable by radar. So really your numbers are probably significantly
Right.
higher.
There is an uncountable amount of smaller debris that we can't account for here. So we've picked low Earth orbit, and we know why. Then we have to pick what kind of low Earth orbit debris is the best choice to deorbit. So the 2 possibilities that we looked at were large inactive satellites, things that have lived out their mission and no longer receive communication. This is a picture of NVSat, which they lost contact April 8th, 2012, and after they were unable to regain contact, so they officially declared the mission ended. So that's one option. The other option is a spent upper stage. So the pictures here are the Cosmos 3, which is a Russian upper stage, and the Agena upper stage, which was it was very common back in the 70s. The Cosmos 3 is important because it's probably the most abundant upper stage in orbit right now. And the Agena stage is like the US equivalent, essentially, of that. So the benefits of the spent upper stages is that they're essentially just structural members. They're designed and built to withstand a load, launch loads. They're not secret. They're essentially commercial things that the government contracted and was never really, classified or anything. It's all been declassified now. With inactive satellites, there are a lot of components there that we're not sure about. They're still classified. They're highly advanced technology. Governments might have a problem, probably would have a problem with us trying to essentially clamp on and deorbit their satellites, even with the US, because we don't know what the government has put on some of these satellites.
Hey everyone, as said before, my name is Jeff. I am the structural engineer for Project Curimba. So Chris has gone over the what, but now we need to know where we're going. So obviously we're in low Earth orbit. We got to know where in low Earth orbit because you've got the entire globe to cover. So this chart shows you the average radar cross sections of objects based on their altitude and angle of inclination. It goes from a radar cross section of 5 square meters, of greater than 5 square meters, as a bold red cross, to a radar cross section of less than 1 square meter as the gray box. Now, as you can see, the majority of debris tends to be concentrated between 96 and 100 degrees of apogee in referred to as high inclination sun-synchronous orbits. Okay, so this slide is a SDK simulation of some of these orbits, which are put into a more visual format so that we can better get a good feel for what's happening while this stuff's moving around. This helps us also design missions, because we got to launch our project up there too. So we got to make sure that, when we're going to this target inclination, we don't hit anything.
All right, so this was touched upon briefly by Chris. The next question is that now that we've decided we do not want to deorbit inactive satellites and that we want to go to a spent upper stage instead, the next question is, what upper stage do we select? We've said this before, that the most abundant rocket body up in space is the Cosmos 3, the SL-8 rocket body. There are about 118 of those in low Earth orbit, but obviously due to national security concerns. Although there has been talk of an international cooperation on such a project, but for national security issues, we've decided to work on a US-owned upper stage. So there are 4 upper stages within 4 degrees of inclination of the SL-8, and these are all to our Agena D rocket bodies. The one that we would like to select for our project is the 1969-082AB, because this has the largest radar cross-section, and at this point our logic is the bigger the body, the easier it should be to deorbit it. So for all the further analysis done, the body we've selected is an Agena D upper stage.
So, just a question,
Yes, sure.
different versions of the Agena, which particular version? Do you recognize about a number?
I'll talk about that.
The Agena D.
Yeah, we'll talk about that right here. Okay, so we retrieved some technical drawings from NASA's technical report server, and we were able to model a Agena D upper stage in a CAD program called CATIA. And using that, we were able to put it into other programs like SDK and DAS for analysis. Okay, so we've covered the what and the where. Now we need to do the how. How are we going to get there? So here's a basic storyboard of our mission. We are going to have the our launch vehicle is going to place our mothership in low Earth orbit on the same inclination as the rocket body in question, and our upper stage is our upper stage for our launch is going to be on its own decaying orbit after it releases. So we're not making more space clutter, because that was one of the considerations that was brought up. And on the next slide, okay. So here's the basic concepts of operation. So the mothership's going to carry 12 nanosats up with it. The mission only requires 6, but we carry more in case something goes wrong with the nanosat and it has to be sacrificed or if it fails. Yes.
What is a nanosat?
A nanosatellite is it's a satellite approximately 6 to 12 U.
Yeah, it's a cube size.
Yeah. Small.
It's a mass. I think it's a mass determination.
Yeah.
So our mothership is a mini satellite, I think, which is less than 500 kilograms, and the nanosat has to be less than 24 kilograms. Sorry. So just anything less than 24 kilograms is a nanosat.
Okay. So the mothership will have a battery of sensors, which it will then approach. It will approach the proximity of the rocket body. Then it will start analyzing its motion for its rate of spin in all 3 axes, as well as other dynamic properties like its moment of inertia and such. It will plan a docking spots and best route for the nanosats to go on. It will then launch the nanosats one at a time, and they will navigate to a soft dock with the rocket body. The nanosats will then broadcast data about the spacecraft using their own sensors back to the mothership, where it will update its dynamic models through a process called dynamic model adjustment, I think is what Andrea said it was called. And then it will, this allows for, because we don't know how much fuel is left over in the rocket body, so this allows for things like fuel slosh, structural weaknesses, things like that, which the mothership then performs analysis on. The nanosats will then fire their thrusters and detumble the target rocket body, and the mothership, once its attitude is stabilized, the mothership will then move in and dock and begin the deorbit burn for controlled reentry.
You said nanosats are they get that classification by their mass, but how does that relate in volume? Is it like the size of a projector or
A shoebox.
Shoebox? Okay.
Shoebox size. Now, our first mission will be a sacrificial mission, where the nanosats and the mothership will enter the atmosphere with it. But future missions are planned to have the mothership move it into a controlled reentry, and then detach and bring the nanosats back with it for refueling and resupplies. The mothership will also be designed in the future missions with its own ports for refueling, repowering, and resupplying, as well as loading of nanosats that may have been sacrificed in the mission.
So basically the idea is that once you get it up there, you can just keep refueling it off like a station
Exactly.
or something, and just goes around getting debris and just dumping it back in the Earth.
Tow truck in space.
So my name is Banke I'll tell you about the advantages of the proposed method. So mostly we rely on the proven technologies and well-understood dynamics, and that's one of the reasons why we picked this method. Second one is redundancies. We have 12 nanosatellites. For detumble and deorbit, we can use only minimum of 6. So we have 6 as a backup. That's the second advantage. And the third one is inexpensive price advantage. We use nanosatellites, and they are much cheaper than the regular satellites. And that was our method. But other companies, like European space agencies, try to use the test net like this to catch the debris and then pull it down the orbit. German EADS uses a robotic arm that matches the angular rate with the debris, and then once it matched, it grips it and then detumbles it, for instance, and pulls it down to the earth with it. The third one is UK's Astrium company. It uses a harpoon method. It just shoots a harpoon, attaches it, and pulls it down. The fourth method that's shown here is the method similar to this castnet, but used by the Japanese space agency. It's called fish net. Just pulls a giant net, and then whatever happens to be collected by this net is being pulled down. And that's it.
Okay, so just a question. So once your nanosats go up there and attach to it to get data, would they detumble it if it was tumbling before
Yes.
the mothership comes in to attach?
Yeah, we have a slide about that later.
Okay.
Alright, so we have been discussing the deorbit and controlled reentry maneuvers that the satellites will be performing. But here's the question: that why would we be spending all those resources on a controlled reentry? So if you look at the picture up there, these are two components that were recovered from the uncontrolled reentry of the Delta II upper stage in 1997. The propellant tank was about 580 pounds and the pressurant tank was 66. These were found approximately 75 miles apart. And while there were no casualties reported in that instance, the potential for damage is really obvious. So due to that, thinking of the casualty damage of such uncontrolled reentries, NASA now has a requirement that the casualty risk from surviving fragments and debris cannot be more than 1 in 10,000. So keeping that in mind, we decided to calculate the casualty risk for the re-entry of an Agena D upper stage using NASA Johnson Space Center's debris assessment software. There are 64 components present in the Agena upper stage, and all of these were modeled. The debris area and kinetic energy of land impact was obtained using DAS. Out of all the components present, only 2 of them are expected to survive re-entry: the propellant tank and the engine, due to their large masses and high resistance to high temperatures. So this is the data we obtained from DAS. The debris casualty area is calculated using that equation given up there. It's a function of the cross-sectional area of the surviving debris and the number of objects. Fortunately for us, DAS does all the calculations and just gives us the final results. In this case, the casualty area for the propellant tank is about 10, and for the engine, approximately 6 square meters. The way that the actual casualty risk is calculated is by multiplying the debris area that DAS gives us with the total average population density for the orbit. And this is done using a very handy chart, again from the Johnson Space Center. What you're seeing there is the average population density as a function of the orbital inclination. The boulder line shows the population density as it was in 2000, and the one up above it is the predicted population in 2050. So following the 70-degree inclination, which is what it is for the Agena D that we're considering, and tracing it up to the predicted population, we get a density of 15 persons per square kilometer. And now we multiply that with our debris area to get the total casualty risk. In this case, for the engine, it's 0.87 in 10,000, which is below the limit of 1 in 10,000. But for the propellant tank, it goes beyond the bounds that are set. This makes it necessary for us to have a controlled re-entry, which can only have a probability of failure limit of 65.7%. If If these numbers are met, then we would be within the NASA requirements for a controlled reentry. So now that we know that it needs to be controlled and what the requirements for the mission are, we can perform a preliminary feasibility analysis on the
All right. So for our nanosats and our mothership eventually, we're going to have to dock with the tumbling rocket body. These are some charts that we found from a research paper. It's listed at the bottom there. Two types of maneuvers they considered were minimum propellant maneuvers and minimum time maneuvers. Just by the title, the minimum propellant maneuver saves fuel, and the minimum time accomplishes it in the shortest time possible, given the thrusts that you're able to produce. For our cases, we obviously need a minimum propellant maneuver because there's no urgency to dock once we're in a relative orbit, and it's important for us to conserve as much fuel as possible, either for being able to reuse them or to save it for the deorbit burn. So we chose the minimum propellant maneuver. The difficulties are that the CubeSat to dock with the rocket body, they have to match the final position on the rocket body and the velocity of that position. So on these charts, the sphere is essentially the rocket body that we want to dock with. The red path is the path of the docking point while it's tumbling, and the green, or the blue path, sorry, is the CubeSat's path. So you have to account for the spin in predicting where your docking point is going to be, in addition to the velocity components of the docking point as it's spinning. So our preliminary results show that those maneuvers are going to take less than 0.5 meters per second delta V per CubeSat, which was within our feasibility limits of the fuel we can store per CubeSat. So using some MATLAB code and an SDK, I coded up that specific minimum propellant required algorithm and ran it for just three different final velocity components. So these CubeSats, this is showing 3 CubeSats starting at the same position with the same initial velocity, and each CubeSat is going to the same final position on the rocket body, but with a different delta V, with a different final velocity component. So play this animation. So the lines there are the relative orbits, and the Agena D is the Agena D orbit there. So it's really important that we match the final velocity because our sticking method relies on us not having too many forces at the point of contact. So, for example, if the rocket body was spinning in one direction, we'd have to match that downward velocity when we're in that final position there. And that would allow our docking mechanism to just latch on and connect. Another thing that's important to note is that when you're optimizing for a propellant, the time is also a dependent variable or independent variable. So these were all set to use the same time, delta t. That's important because you can set delta t as the time as large as you want. It'll just take a lot longer, but it might save fuel. So we're going to have to, in the future, make some decisions regarding how fast we want to dock versus how much fuel we're going to use. So you can see all 3 satellites are about to complete the rendezvous.
Okay, so, hey everyone, I'm back. So now that we've discussed how we're going to get there, now we got to attach to it. So initially we looked at a lot of things. The problem was that the Agena D is actually made from a material called magnesium, which is actually a magnesium alloy called AC31, which is non-magnetic. So the easiest way to do it is, of course, either put a bunch of glue on it and slap it on, like some of the proposed methods, or stick to it with a magnetic grip. That won't work on this situation because magnesium itself does not have any, it has 4 valence electrons, meaning it's non-magnetic. So we searched around for a bit, and we came upon a device called the Sticky Boom, which was built by Altius Space Machines. And they have quite a bit of success with attaching to any number of materials, both magnetic and non-magnetic. And this was looking really good because it was a pre-made device. We could just slap it on the satellite and be good to go. We had to abandon this idea, however, because of difficulties in acquiring it. So we looked at alternative solutions. Now, of course, my video is not going to work. So we didn't want to scrap the entire idea because it was a very good idea. So we decided to throw away the arm and keep the sticking grip. Now, the sticking grip works through a principle called electroadhesion, and I have to apologize. It's a YouTube video, and the internet here is not working right now. Now, this is a robot that was designed by SRI International, who has pioneered the field of electroadhesion. As you can see, this is a concrete wall that this robot is sticking to, and it's climbing quite well. Electroadhesion is an electrostatic effect of the friction between two surfaces exposed to a magnetic field. This SRI has done a lot of tests with their robots and other gripping surfaces using electroadhesion, and they have produced results in the range of 0.5 to 1.5 newtons per square centimeter, or 0.8 to 2.3 psi, which is well within our limits for what we need to create for sticking force. As shown in the video, the surface is not magnetic at all. As a matter of fact, SRI's robots work on wood, glass, stucco, concrete, textured surfaces. They've even done it with things like dirt, dust, paint, everything you can think of. Now, the benefit of using electroadhesion in this method is that A, it's conformed to the surface well, B, it's very strong for its power requirements. The robot ran on a lithium-ion battery and was able to carry its own weight and an additional 5 kilograms on just that battery. Additionally, because it can attach to any surface and it can form to any surface, we do not need to create a new gripping head for every mission that we go on. So this is my baby. We affectionately call it the TARDIS. This is the fully designed nanostat. As you can see, there's electroadhesive panels on the bottom, which will deploy once it is released from its deployment container upon the signal from the mothership. Each one of these surfaces is a solar panel, and so the nanostats that we've designed combine compactness, ingenuity, and innovation. Because we use the electroadhesive surface, these panels, they're modeled as stiff plates, but these are actually pretty flexible material. The SRIs actually developed materials that can bend as much as 180 degrees and still be used as attachment methods. So obviously we can't have it doing that when we're flying around. So the panels will have a semi-rigid frame inside which will hold its shape during maneuvers, but still allow enough flexibility to have to form to the surface of the satellite once we attach.
Is there a minimum surface area that has to have attached to the side?
Based on our calculations, we need approximately 0.1 newtons of gripping or force to hold on during our maneuvers, and we have approximately 400 square centimeters. of gripping surface, give or take a couple. So we have more than enough with this.
Now I'll talk about the dynamics of the of the rocket body and the detumbling methods. So this is a general picture of how we'll dock our satellites and detumble the upper stage. In order to detumble the rocket body, we must understand the dynamics of the system. So we model the rocket body and satellites in the MATLAB environment using the toolbox called Simulink and Simulink. So as you can see here, this is the main body of the rocket, model as a cylinder. We model the engine and nozzle part as a cylinder as well, just for the simplicity and because Simulink it has only cylindrical shapes, brick shape, and spherical shapes. And this is one CubeSat. So we model the connection between CubeSat and the rocket body as a torsional spring damper system. Because in reality it's not stick like rigidly with bolts, it just moves a little bit around. It's loosened. So after that we run the simulations and we see these results. This is just a preliminary results that shows that using the torque as the thrust produced by the CubeSat of 0.1 Newton for 2 seconds, this is what we get from the simulation. This is the angle between the nozzle and the rocket body. This is the twist between this cylinder and this cylinder. As we can see, the twist is not very big. It's like less than 1 degree, and it damps out. That's good because after the maneuver, it becomes stable and there is no unaccounted dynamics. The same happens with the deflection angle between the nanosatellite and the rocket body, like between this and these two frames. As we can see, the deflection angle is even smaller, so on the order of 10 to negative 4 degrees, and it damps out too. Okay, this shows that we can use this model, but this model doesn't include the disturbances like aerodynamic drag, electromagnetic interactions, and gravity. Later on we'll include that.
But you're only applying thrust for one short little minute there, one short moment.
It's like 2 seconds, just for the simulation. After we have the full model with all the 3-axis rotations, we can determine exactly what period of time we need to thrust our satellites. For now, it's just for the simulation process. Okay.
All right. So the last part is actually deorbiting our satellite, and this chart comes from the NASA technical document for requirements for deorbiting satellites. We want to be able to aim our deorbit because we have to have a controlled deorbit. That means we have to fall in the immediate reentry or the targeted reentry areas of this graph. And we're also limited by our altitude. It's 1,000 kilometers roughly. So from this chart we just pulled that our delta V for deorbiting has to be between around 200 to 350 to be in that immediate reentry area. So this is just a really very preliminary SDK simulation running our deorbit for the rocket body. So here it's running at like 40 times speed, and then it'll slow down as we get closer. You can see our targeted landing ellipse right there, and it's rotating under to get closer to our orbit. So this is the final pass, and right around there we're applying our deorbit burn. So you can see how quickly it'll deorbit after we apply the burn. So our we don't have any analysis yet, but we're going to run a Monte Carlo analysis and vary a bunch of variables to find our actual landing ellipse. Now the landing ellipse is the ellipse of, I think, 1 or 2 standard deviations where we predict all of the debris will land. So you want to put that landing ellipse somewhere where the people don't live. So looking at the video, this frame, the targeted landing area is the area between California and Hawaii, going up to Alaska. So it's basically this area here. And that fits some NASA requirements, like we have to be 300 miles away from the coast, and some other things like that. There's different numbers for foreign coastlines, but this is the biggest landing area that's on our orbital inclination. And here's another video just showing from the Agena stage point of view. So this will just go through one orbit, and then it'll do the deorbit burn. Slowing down the simulation. And then you can see that was the deorbit burn right there, and we're separating from our previous orbit path. And SDK has some basic atmospheric models in it, but to get a more accurate one, we're going to have to make our own atmospheric models and vary things like the atmospheric density, which you can never predict accurately. So the Monte Carlo simulation would essentially just be varying those variables and seeing where that affects our landing area. So summary, everything we talked about. The orbital debris is very dangerous. It's a problem that's going to get worse, and we need to solve it. We chose to start with large objects in the low Earth orbit. We also chose rocket bodies because the benefits are they're robust, and there's no national security concerns, really. Then our mission was a demo mission to the Agena D upper stage. The final goal would be to get the Cosmos because it's much more massive and there's a lot more of them in orbit. So just the Agena D stage of this is proving that we can do it. And hopefully, eventually they'd let us do a Cosmos, and that's 200 objects almost you could remove from space. They're like 1,000 kilograms each, like 1,300 kilograms. And then, yeah, it's based on multiple satellites, and they cooperatively detumble, so most of our work was already done for us previously. We're just designing algorithms really and proving that it can be done. And we talked a bit about our future goals before, having the reusable mission and refilling our propellant tanks. So, any questions?
So if the Earth is here and you got a piece up here in this kind of orbit, does it have to kind of stay in that orbit, or can you direct it a different way? Or
orbit change maneuvers are really delta V intensive. It's the most delta V intensive change you can do. It's a lot easier to change the height of your orbit.
Okay.
So it's really unfeasible for us to be able to change the inclination of the orbit. It's not something we really looked at seriously. Anything else?
Are the adhesion panels, are those just the pedals that open, or is the bottom of the design, is that also part of that
the
panel?
bottom is, you can't see it in this model because I wanted to show you guys the whole thing. And I actually tried showing you guys the bottom too, but it looked horrible. There's actually a small surface in the center of it that is a central contact point for the electroadhesion. That is also part of the electroadhesive surface. And then the bottoms of these panels here are also electroadhesive.
Right. So I figure you're probably hitting a curved surface.
Yeah.
That was part of the problem that was discussed in a lot of the early problems brainstorming. Was we got a curved surface and a flat plate. How are we going to do this? But as I mentioned earlier, we have a semi-rigid frame. So what happens is, actually we went through an interesting stage where we actually thought about having an electroactive polymer help us form it to the surface. But we didn't go with that because it was too unproven. And we couldn't get our hands on any as well. So the electroadhesive actually acts similar to a magnet in that once one part attaches, it'll pull the rest of it with it, which will then start attaching and it'll cascade down until the whole plate is gripping. Additionally, because it's flexible in multiple directions, it doesn't matter which of the plates lands along the length of the spacecraft, or even not at all. This could be tilted 45 degrees or any other degree angle from the parallel to the surface. So they can form well to the surface no matter what. Any other questions?
So this nanosat, besides it attaching to a genus, it can also probably get smaller stuff too then, right?
In theory?
We haven't designed for anything smaller, honestly, because capturing smaller stuff is difficult. With the GINA, it's a known orbit. It's something we can like look up online or track from ground. With the smaller stuff, that you're getting to like the CastNet proposals and other things like that, it's a lot harder to collect too because you can't see it too.
Sounds like there's no one way to do it all. There's probably going to be several proposals to collect all the debris.
Right.
Okay.
Smaller stuff is a big danger too because if it's one of those things that if you don't get it early, if you wait too long and there's just small stuff everywhere, you'll be launching rockets and they'll be destroyed on the way up or with things you can't even see.
Yeah, I'd like to see somebody catch one of those booster rockets with a net.
Yeah.
So is Gravity your favorite movie?
It's our professor's favorite movie, I think. I haven't seen it yet, so.
Were there any other questions?
Have you considered that the upper stage might be tumble a lot when you approach it?
Yeah, our simulations are run with the predicted maximum tumble, which is 10 degrees per second in every direction. So it's tumbling 10 degrees per second around its x, y, and z axes. And that's actually drawn from a lot of other papers. There's been research into that, like to see what the rate of tumble is for these things. And most of them agreed that 10 degrees per second was like the maximum you could expect. There's a lot of things that factor into that, like if it's skimming the surface, it'll kind of get like more friction on the bottom than the top, so that can introduce tumbling. Some of those are also stabilizing effects, so gravity gradient will tend to like align it along, I think, the
major axis of inertia.
Yeah. And other things also influence it, solar radiation. But yeah, 10 degrees per second in all axes was our estimation.
And your approach will work when you fly to it and try to attach.
Yeah, that's the importance of getting that final velocity at the docking point. So that's why we have our initial relative orbit. Our mothership's going to find the attitude and be able to predict. So let's say our nanosat's going to take 1,000 seconds to get there. It's going to predict 1,000 seconds ahead. So it's going to know, for example, like the rocket body's rotating in this direction. So that means our docking point we want is right here. This docking point's rotating in this direction. So we can tell our nanosat to basically approach from this direction and match the velocity at this point. The danger there is missing, and you just would keep going in that direction.
Additionally, the nanosats themselves have sensors on board which can be used, which will be updating and replanning their flight path in situ.
Yeah, because if you miss, then you're causing more space debris.
Yeah, that is a problem. But at least our nanosats would hopefully still be under our control and would be able to withdraw them or even deorbit them by themselves, hopefully.
Yeah. So when you do attach it to the main ship, your mothership per se, what happens to the nano ones? Do they go back, or do they just stay on there and burn?
With this proposal, the nanosats are all going to stay there and be deorbited at the same time. So the entire thing comes crashing down.
Even in your future?
In the future ones, the nanosats, after the mothership docks, the nanosats would undock, return to the mothership, then the mothership would deorbit and detach and go away.
Okay, that's what I was wondering.
Okay.
Yeah, but I do like your idea. I think it's pretty good.
Yeah.
Cool.
Yeah.
Okay.
Do we want to have this in the picture? Or just in the second?
Have the title slide?
that one works.
No.